Newton-like units. Numbers go in, they get multiplied by whatever weight we have on each of these lines. They get summed together, and that's what comes out of this circle. Well, numbers come out of these circles and get multiplied by whatever weights we have on these lines. They get summed up inside of these circles, and then that number comes out of here and gets summed up inside of this one, and the number comes out of here, and that produces the output. And behold the artificial neural network. That's what it is. This is what you're evolving in this assignment, is you're evolving the weights in this artificial neural network. And once those weights get reasonably well trained, this artificial neural network presumably takes these inputs, thinks about it, where thinking about it is defined as do a bunch of math, and then some number comes out that tells which direction to go and how much impulse force to use, and that makes the sumo ball knock the other sumo ball out of the circle. Okay? Do you kind of get artificial neural networks? They're actually not super complicated. If you were to actually express the full equation for it, though, it would look really nasty and would fill up the whole chalkboard, but drawing the picture is not so bad, right? Okay, well, that's an artificial neural network. One more complexity to add to it. Turns out, every one of these layers is the equivalent to a linear operation. So if you take those inputs and multiply it by a 2x4 matrix, you get the outputs of this. And if you take those outputs and multiply it by a 4x2 matrix, you get this output. Multiply it by a 2x1 matrix, and you get this one. So it's really just a bunch of matrix multiplication operations. Yeah.
Is there a difference between this and what they call the deep neural networks?
So, yeah, there is a difference, although it's actually not very well defined. By deep, essentially, they mean got a lot of layers. So imagine this one has 4 layers. What if I add 3 more layers? Is it deep yet? Getting there. Sure. Essentially, a deep neural network is just a neural network. The word deep, it spawned a whole craze of excitement, but in reality, what made deep neural networks work really well is we figured out how to parallelize these things on graphical processing units. And because of that, these train amazingly fast, and they do really cool things, and deep has nothing to do with it. Deep's just a word, but they do work better when they have a lot of layers, so that word really took over as a massive buzzword. What I've shown you so far is almost right, but in fact it doesn't actually work. Because, how much time do I got? 10 minutes, that's just enough time. Okay, if you take a linear function of a linear function of a linear function, what does that make? A linear function. The thing is if you take 2 linear functions, you can reduce them to 1 linear function. In other words, this neural network is no more powerful than a 1-layer artificial neural network. However, if I change the values by some nonlinear function, then it does weird stuff to the weights. So instead of the form equation being y equals sum of w sub I times x sub I, this is what I told you the equation was. We're just going to change that to y equals the hyperbolic tangent. Just because hyperbolic tangent is nonlinear and it's really weird and it's hard to think about, now this neural network becomes infinitely more powerful. And we can actually prove that the addition of this little weirdness makes this thing super, super powerful. Now, it doesn't actually have to be the hyperbolic tangent. People have tried doing sine. And in fact, I have a paper under review right now that uses sine, and it achieves amazing results at time series forecasting. And we've used all kinds of other functions. You just have to use something that's nonlinear. I'm going to go back to tan h because it's probably the most popular function. And if you make this be the equation inside each of your units, by the way, this is what the plot of it looks like. That's why I drew that S figure there. This kind of bends the numbers in some nonlinear way. Well, now the math is just crazy complex, right? It used to be linear, but now it's the hyperbolic tangent of some linear thing, and then every layer is going to do hyperbolic tangent again, and it just gets unwieldy, right? But that means this thing can represent all kinds of amazingly complex and intricate functions, and that gives these neural networks a lot of power. Okay? So
there's some amount of weirdness, that function that you're, the hyperbolic tangent or sine or whatever, one of those would be like an ideal, give it the most power, I guess, as you're saying.
So this is what's called the activation function, the 10H. And yeah, the ideal activation function would be the one that fits perfectly to whatever function you're trying to fit to. Because then all you'd have to do is have all the weights just be identity function, and it would perfectly fit to it. In the real world, though, you never know the function you're trying to fit to, because if you did, then what problem are you trying to solve? So nobody knows what activation function is best, and essentially it's been proven that it doesn't matter what your activation function is, as long as it's nonlinear, then a network of sufficient size can represent any possible function. I'll even prove that for you in a minute, and we'll see that. Probably not today, because we don't have a lot of time. Yeah?
Could we figure out which one our brain uses?
Yes, we can. In fact, it's very, there are approximations to it, but 10H is kind of a vague approximation to it. And so that's another good reason, is it's slightly biologically plausible. So if you use 10H, then these things behave a little bit-ish like neurons in your brain. Of course, we got to get back and qualify that the ones in your brains are doing these spikes that happen over time, and there's all kinds of additional parameters. For example, the neurons get tired and they can't spike above a certain rate, and they're affected by chemicals in your brain, and there's all kinds of complexity that these don't have. But if we can get away from that complexity and we represent the spikes in frequency form, then 10H is pretty much close enough that we can say, hey, as long as the firings is really what causes your cognition and your thinking, then this is close enough to do it, and we should be able to make computers do it. This does not attempt to be a brain. So this is not biologically plausible, but it's biologically inspired, we'll say. It's kind of, we've taken the meat out of biology, and now we're going to do what works in artificial intelligence and forget about biology. There are, of course, entire branches of people that study the biologically plausible models, and you can build actual models that try really hard to simulate brains like they really are, and those are kind of cool. In fact, let me use my last 4 minutes to show you the Open Worm project. Okay. Open Worm. Anybody seen this before? Okay, so there's a creature called the C. elegans nematode roundworm. It happens to be the simplest creature that we've been able to find on planet Earth that has a nervous system. So I don't remember the stats about it. There's a whole Wikipedia page on it. We could go read about it. There's only something like 900 cells in the worm, and 200 of them are brain cells. And that's cool because it's so simple that we can actually simulate the thing. So here, let's watch a video. I don't have audio hooked up. Well, basically, this is a simulated worm. And what's interesting is it's behaving like the actual C. elegans nematode roundworm actually behaves in the real world, and yet this is a simulation. So we can take these roundworms, which you can only see under a microscope because they're very tiny, and they do some rather intricate stuff. They find mates, they pair up, they reproduce, they seek for food, they eat it, they digest it, and they wiggle. I mean, they don't log on to Facebook or anything, but they do some interesting things. And we've been able to achieve what we believe is the same behavior in simulation. And so essentially we've created the first completely 100% synthetic life form. Isn't that just pretty awesome? Now, it's not simulated all the way down to the atoms. There are things that go on in these cells that we cannot simulate. It's just too complicated. But at least at the level of the synaptic connections between the neurons, it's using spiking, simulated spiking neurons, just like you have in a biological brain, and it's behaving at least to some level of approximation, although the same way this thing does all the way down to the cellular level. They've actually been able to plug this into robots and get the robots to do weird things that somehow mirror what the worm would do in real life. And so we've almost brought to life the first cybernetic creature. Now we just have to get from 200 neuron cells to the 100 billion that humans have, and then we better watch out, right?
So is it wrong to stop the simulation?
What's that?
Is it wrong to stop the simulation?
Yeah, is it wrong to stop the simulation? I don't know. What if you created the simulation? Doesn't that make you God? And is it wrong to duplicate the simulation? This gets so complex at some point. I don't know. I'm going to say that I don't care if a roundworm dies anyway. So, I mean, they cause horrible, debilitating diseases. Who wants a roundworm? Oh, and here's a promo about...
I'm Steven. About 3 years ago, I had a crazy idea. I was sitting at home.
Okay.
I was sitting at home watching Star
Stop.
Trek.
Feel free to go read about roundworms and all that kind of thing. Thanks for coming. See you next time.